Okay, well, let's kick off and ask Pierre, have you got any comments on the content of that one?
Yeah, I think it was an excellent video. It's very well explained. I think it's one of the best we've seen so far. But while I've got, shall I say, the floor or the mic, I'm going to show you something on my camera.
Yeah.
It's a book called Big Bang by Simon Singh.
Oh, yeah.
Which is an outstanding read. He's obviously a mathematician, and it gives a fantastic overview of the whole history of the Big Bang model and the big tug between steady state and Big Bang. And in a nutshell, which did come out of this video, Alpha and Gamow was the supervisor, actually did most of the initial Big Bang nuclear synthesis. Beta was added as a joke, and it sort of backfired. But ironically, the guy that really contributed to understanding where the heavier elements came from was Fred Hoyle. And I'm actually going to scan one page 388, which is a table which was calculated by Fred Hoyle to show the temperatures and the densities required for different elements to fuse. Remember, he was the first one to use the term Big Bang. He regarded it as a derogatory term, but it stuck.
Yeah.
He was a very, very big steady state man. And in any case, I've got a whole host of books like this, which was given to me by ex-colleague's son. And I think I'm going to resend to Peter and ask Peter to resend, well, to all our membership, anyone wanting to read this absolutely excellent collection of books or to borrow them and return them is more than welcome. But this is one of those which I would very, very strongly recommend. But overall, I think it is a fantastic video, and it gives a realistic overview.
Okay, thanks, Pierre. It was perhaps quite a lot for most of us to take in that aren't very familiar with the topics and so on. I do have a transcript. I just want to pull that up quickly. Where is it now? I'm just going to open that and then share it. But I'll send this through to everybody as well. Where is it now? Where is it? I don't see it.
Derek, can I just add one more thing? I did say at the start of the talk that there is a very excellent tablet at Gearing's Point explaining the origin of all the elements. I'm going to send the original PDF document to Peter to send to all the attendees tonight, all the cosmologists.
Okay.
Because it's very interesting. And I must also just add one interesting fact. We were at the star party at Leeuwenbosfontein when the first neutron star merger was detected through gravitational waves. And within 2 weeks after that, the new periodic table, which explained where heavier elements came from, became available. So I'll attach that to what I sent to Peter for onward distribution as well.
All right. This is the transcript. I made some corrections here. There was one question I had in my mind where he mentioned with Rutherford's colleague Blackett, where they bombarded nitrogen with alpha particles or something. And this, you first said, oh, they created hydrogen, and then a couple of sentences later it said they created oxygen. So I thought they made an error, but I went and just checked on Wikipedia on this Blackett guy. What did he actually do, and what was created when they did this? And just reading that, it says they bombarded nitrogen with alpha particles, and it first formed fluorine, which then disintegrated into an isotope of oxygen-17 and a proton. So of course, a proton is hydrogen, and then so that's possibly, you should have just mentioned that they created oxygen and hydrogen. So I just wanted to mention it. All right, anybody else got any questions? I see David and Elena got a hand up. Oh,
sorry, hi, David. Just maybe Pierre can just help me out. I once had a lecturer who was, he was fascinated by the Big Bang, and in particular, he was fascinated by the binding energies. And so, if you plot the atomic number against the different elements, then that binding energy obviously peaks out with iron. But after helium, there's a huge dip towards lithium. And I've never quite been able to understand that. Everything goes exponentially up, all the binding energies, and then all of a sudden at lithium, it just plummets. Pierre, maybe one of your books could explain that to me.
Yes, I will make a few comments. Simon Singh spends quite a lot of time on explaining that, and that is the reason that I think it is it 5 or 7 nucleon gap, which could not be gotten over through the Big Bang nucleosynthesis. And it's explained in detail in Simon Singh. But that's why you've got to understand between Big Bang nucleosynthesis in the first 30 minutes or 300 seconds, I think it was, and then what happened when the first stars went supernova and distributed heavier elements. You couldn't progress. There was a problem. I think it's either 5 or 7 nucleon. Look up the story, and it did prevent Big Bang nucleosynthesis going to elements heavier than lithium, just hydrogen, helium, and lithium. So it is a well-known problem. That dip in the binding energy per nucleon is very real, and it was a problem. But it's very well described in Simon Singh's book. Maybe I can scan a few of the relevant pages and send to Peter as well.
Oh, thanks, Pierre. That would be great. Thank you very much.
As I said, I will send the transcript to Peter, who will distribute it to all the attendees. So perhaps, because he does go over this, it is quite a lot to take in one shot. So maybe reading it slowly through in the transcript will help a bit. But then, yeah, if I remember correctly, the theory is that, in a star, elements up to the weight of iron can form, and beyond that, the fusion energy is negative, and nothing heavier than iron can form in a star. So, I mean,
that's correct.
How does that fit in with the whole not getting beyond? Was that just at the Big Bang before, not in stars, just at the initial formation of elements, that this lithium is a problem?
Now, the heaviest element that can be formed within stars through fusion is iron. But when it goes supernova, you get much higher densities and compression, and then heavier elements are formed. So that's how the universe was seeded, by basically all elements heavier than iron, and in our bodies as well. I mean, our sun is a population 1, in other words, 3rd generation star. And all the elements heavier than iron were recycled through a supernova in the past. So, just to repeat the statement, all elements heavier than iron were created or recycled through supernova explosions.
Okay, and that collision of the neutron stars that he mentioned, will they actually found for strontium in the signature? How heavy is strontium? Is that quite a heavy one?
Yes, it is. And in fact, if you look at the periodic element table that is at Gehring's point, and which I'll send to Peter, you can see how many of the heavier elements were actually formed in nucleon star collisions. It's absolutely amazing.
Mm. Okay, I think I've got that on my computer somewhere. I must dig it up.
You do have, but I'll send it to Peter again.
Oh. Right. I had another question. I've just forgotten what it is. I'll think of it just now. Have a look
Just
at
one comment. I wasn't aware that of the fact, and this is ignorance on my side, that brown dwarfs could actually undergo fusion. And I quickly Googled, and they do. And he mentioned it in the video clip that they can actually, because of helium-3, they can actually fuse. But there's very little helium-3 in a brown dwarf, so that happens for a very short period. And thereafter, there's no fusion in a brown dwarf. But I wasn't aware that they can actually undergo some fusion.
although, I mean, a brown dwarf does emit some light. So I mean, that energy for that light must come from some fusion, shouldn't it?
No, it's just gravity which collapses, brings them together and raises the temperature, but not sufficiently.
Okay. All right. Okay. Right. All right. Any more comments? Using a couple of participants here. All right. Okay, if there's no more, I presume everybody's hungry and they want to go and have supper or something. So thanks very much for your attendance. And if you think of any questions afterwards, I mean, one always thinks of these things later and you think, oh, I should have asked this, should have asked that. You're welcome to email through, we'll respond to those.
Simply fascinating. Thank you.
Derek and Peter, can I ask you just to hang on a while after the rest have left the meeting? There's something I want to discuss with you.
Sure. Okay.
Thank you, Derek.
Thank you.
Yeah. Bye-bye.
Thank you, Derek.
Thanks. Enjoy the rest of your evening.
Yeah, thank you. It was most interesting. Thanks. A couple of questions, but leave it for later. So thank you.
You can shoot a question quickly if you want now. You're welcome.
Oh, all right. Pierre spoke about recycling, and can you recycle a heavy metal in a low density environment like the planet Earth? And why is the sunlight white? Is it we recognize it as white because every element has got their own particular frequency of what do you call it? The bands, the color bands. So how perfect is it that we get white light from the sun, and are all the bright white stars, are they all giving out perfect white light, or have they got their tinges?
Yeah, do you want to answer that quickly? Or
I'm going to answer it in two different ways. First of all, the temperature of a star, or the color of the light emitted by a star is very differently determined by temperature. The bigger and the hotter it is, the bluer it is. And the cooler it is, the redder it is. Now, the sun is a G2 star. Its spectrum peaks at 5,700 centigrade. So that's sort of yellow-green. We regard this as white light because we evolved over it over billions of years. And that is a mixture of all the different wavelengths that you find in the radiation emitted from the sun. And I think we describe it as white, because that's the mixture that we get. And if we reproduce that photographically to red, green, and blue, we also reproduce white. I hope that answers your question.
Yeah, no, thanks. Yeah.
But just by the way,
Yeah.
the frequency of our star is in fact the dominant frequency is in fact green, but it doesn't look green to us because on either side of the green is the blue and the red, which are the blue and the red are equal in intensity from the sun, and that combines with the green to actually make it look yellowish. But the green is actually the most abundant frequency emitted by the sun. And as Pierre says, different sizes of stars create different temperatures and different stages of development and so on. Also, whether the gas is expanded and all that sort of thing. So yeah.
Well,
okay, I hope that didn't confuse you even more. Do you agree with what I said, Pierre, or have I got it wrong?
I feel enlightened, but
Confused.
Completely. Yeah.
You need to look at a lot of our displays at Gearing's Point explain a lot of this.
Yeah.
Right, thanks everybody.
Thank you again very much. Bye. Night.
Thank you very much.
Night.
Right.
Please keep recording, Derek, when Pierre wants to speak to me, because I probably got a whole list of stuff.
All right, what I'm gonna do is I'm gonna stop the recording and then start recording again.
Okay.
Different to report our discussion.
Just a second.